Okay, let's continue from where we left. Let's look at example number 5. Show that W is equal to B, which is a polynomial, is an element of the polynomial. And they say that the bigger polynomial is actually the polynomial with real coefficients. So how can we prove that it is a subspace of a P? Is a subspace. So what we do is we use a subspace test. So we start from the zero function. So we can prove this. We know that using the polynomial, using the subspace test, then since the zero polynomial, which you can put like that, capital zero, satisfies zero and then the zero function of that, which is equals to zero, then zero polynomial is an element of W. So that is the first part. So you start from the zero polynomial. So zero polynomial is an element of W. Now, if we let, or you can say since, or we can let P and Q to be the element of W. We let P and Q to be the element of W. And C and D to be elements of real number. Then CP plus DQ. And then we put this zero polynomial, zero there, is equals to CP 0 plus CQ 0, which is equals to C0 plus D0, which is equals to 0. Which is equals to 0. So CP plus DQ is also an element of W. So therefore, by subspace test, then W is a subspace. So it starts from 0, then we now come to you have polynomials, which is P and Q, which are in W. Then CP plus DQ of 0 is the same as CP 0 plus CQ 0, and CP 0 is equals to 0. It's also the same as Q 0 is equal to 0, and C 0 is equal to C 0 there. So therefore, CP is an element of. Okay, let's look at another definition here, which we already did. And I think I also said give you this one in our exam definition. If we let V, the capital V, be a vector space, V1, V2, and these are vectors all the way to VP, element of V, and C1, C2, all the way to CP, element of real numbers, and these are weights. Then, one, the expression C1 V1 plus C2 V2 plus CP VP is called a linear combination of V1, V2, all the way to VP, where the scalars C1 all the way to CP are called the weights. Two, the set of all linear combinations of V1 all the way to VP is called a span of V1 all the way to VP, which we can write as the span of V1, V2, all the way to VP equals to C1 V1 plus C2 V2 plus CP VP, such that C1, C2, all the way to CP are elements of real number. This one we already did, this definition. So we had this one in the previous section. I also gave you this one in the first example. So the linear combination is when you combine, when you add the weights plus the polynomials. The vectors, and multiply the vector, and these are actually the coefficients, C1, C2. So those are what we call the weights. Now, the linear combination of that can also be written as the span of V1, V2, where this is actually the linear combination. So we bring together the vectors. Okay. Let's look at another example. Example number 6. Find the span of 1x squared all the way to xn in the vector space, the polynomial with real coefficients, where n is a non-negative integer. Find the span of that. And this is a polynomial with real coefficients. So previously we say that the span is actually the linear combination of the vectors there. Then it is similar to the one for polynomial here. So therefore, the solution here, the span of now this, which is 1x squared all the way to xn. So this is xn, is the same as a0 plus a1x plus a2x squared plus an xn, such that a0 A1 all the way to AN are elements of real number. So it's just like that. So that is this part of that. So we always write. So this is the same as the polynomial. Let's look at a theorem here, which is the same as the theorem which we did in another section. The theorem. We said if V is a vector space and V1, V2, all these are vectors, all the way to VP are elements of V, then span V1, V2, all the way to VP is a subspace of V. Is a subspace of V. So here you just use the subspace test. So you just use the subspace test. So let me give you a sketch, but you can still find this one in your textbook. So sketch of proof. So what you need to do is you can let W to be equals to the span of V1 all the way to VP. Okay. Can let that to be that. Now, since 0 vector is the same as 0 V1 plus 0 V2 plus 0 VP, then 0 vector is an element of what? Element of the. So that is a first rule. So you start by the 0 there. So you realize that this is also in the span. Then you can also let the next section, you let U and V to be the elements of W. That's that and that to be the element of W. Then you can also take C and D to be the elements of real number. Yeah. Then you can say you can take actually C and D to be, so we can actually say C1, C2, up to, let's say, CP, and then D1, D2, up to DP are elements of real number. Yeah. Then you can say U to be equals to U1, C1. Actually, C1, U1 plus CP, U, UP. And then also you can let V to be equals to D1, U1 plus all the way to DP, U, UP. Then you come and add. So you add the two of them. So you can add U plus V there, which is the addition of this. And all these are elements of W. So they are elements of W. So therefore, using the subspace test, then V, the vector V is a subspace. The span of this is a subspace of V. Subspace of V. Okay, now let's look at the notation here, which we already defined. We can define the capital P to be equals to the span of 1 x squared all the way to xn. And this P is the polynomial with real coefficients, which is the vector space of all polynomials with real coefficients of degree at most n of degree. So we most of the time use this, and this is a polynomial of degree at most n. So it has the real coefficient, the real coefficients. Let's look at another example here on the subspace example. Show that W is a subspace of R3. Show that W is a subspace of R3. And if we have this W to be equals to 3A minus 2B plus C, and then here A plus 2C, and then we have B minus C, elements of R3, such that A, B, and C are elements of real number. Show that W is a subspace of R3. So what you need to do is you need to look at the linear combination of this. So what is the span of this? These are actually the linear combinations. So what are the span of that? So to write these in a span form, then we can write this one as W to be equals to. So the solution W to be equals to. So we can factor out A here. So A, and then we have 3 there, and then we have a 1 there, and then the last one there is 0. Okay. And then plus our B to be now minus 2, 0, and 1 there, and then plus our C to be now 1, 2, and minus 1. And these are, we want to see whether these are elements of what? R3, such that A, B, and C are elements of real number. Then therefore, this is actually the same as the span of the vectors now, which are the vector 3, 1, 0, and minus 2, 0, 1, and also 1, 2, and minus 1. 2, and minus 1. So it shows that is a subspace of R3. These 3 are actually the number of entries here. So the number of entries, they should be 2. So we can see 1, 2, 3. So it's a subspace of. Now, number B. if you're given W to be equals to minus A plus 1, 2A plus B, and then B plus 2. Check whether this one is an element of R3, so that A, B is an element of real. So how can we see whether this one has 3 edges? So what we can do here is, for the solution, we can let A prime to be equals to minus A plus 1. Okay. A prime to be equals to minus A plus 1. And then we can also let this B prime to be equals to B plus 2. Okay. So that A, then A can be equals to, so we can take this one here and then we bring this one, A to be equals to minus A prime plus 1. And then our B to be equals to B prime minus 2. B prime. Then for W here will now be equals to, we already use this one as our A prime. And then we have our 2A is minus A prime plus 1 plus our B, or B is B prime minus 2. And then our last one here is our B prime. B prime. So we want to see whether this is an element of R3 such that A prime and then P prime is an element of real number. Then our W now will now be equal to, so our A1 there, and then when you open these brackets here, then what you get is, so this is minus 2A prime, and then this is 2 and this 2 here, yeah. So this 2 will cancel with this 2 here, right? And then we have a what? Plus B prime there, plus B prime. And then this is our B prime over there. So we want to see whether this is element of R3 such that A prime, B prime is an element of real number. Then this is equals to the what? The span of, this is equals to the span of, for A1 there. So for A1 there, we have what? 1, and then minus 2, and then the last one there is 0. And then for B prime there is, we have our 0, we have a 1 and 1. So that shows that they have the entries there. So basically, this is our element of R. Element of R. I skipped one part. So we can go to that, and then come back. Any question up to that? Okay, if you don't have any question, then let's go to the next section, which is section 4.2, the null space. The column spaces and linear transformations. And linear transformations. So we have actually looked at this most of all of these actually in our previous section. So we'll just go through it so quickly. And let's start from the first section, which is the linear transformation. The linear transformation. If we still remember, what did we say about the linear transformation? So let's look at the definition of a linear transformation. If we let V and W to be vector spaces, to be the vector spaces, a transformation which you can put as T from V to W is called a linear transformation from V to W if T of U plus V is equals to TU plus TV, and T of CU equals to CTU for U and V elements of V and C element of real number. So we define this one last. Say we have this and that, okay? So there is a transformation here. There is a bridge here, which you can use as T. Okay? Then if we have the elements here, which is V and this one is W, then if we have the elements here of, let's say, U and V, these are actually vectors. Then if these elements are in V, then the transformation here will be TU and another one somewhere there, TV, okay? So it is transforming, so this U transform to that, and this V transform to that. So TU and TV are elements of W. So they are actually in W, and U and V are in V. So the transformation T from V to W is written as TU is TU. Okay. So those are in W. So that is a transformation. We actually did this one previously. So let's look at another theorem here, which we already proved last time. We will not prove it, we'll just tell it, and then you will go look at it in your textbook. If we let V and W be vector spaces, a transformation T from V to W is a linear transformation if and only if CU plus DV is equals to CTU plus DTV for any U and V elements of V and C and D elements of V. So in this case here, we have actually, instead of doing this, we actually convert. So this is a linear transformation also. This is also a linear. So if we multiply the constants, so the scalars by the vectors, then it is the same as CT plus B. So you can still do other vectors. We prove this on previous. Okay, let's look at the first example in this section. First example. Example number 1. A. Show that the transformation T from the polynomial n Pn to Rn defined by T A naught plus A1x plus an minus 1 xn minus 1 plus an xn equals to A1 an minus 1 an for A naught A1 an minus 1 an elements of real number is a linear transformation. Is a linear transformation. So we have the polynomial is Pn. Now show that this polynomial, when you transform this polynomial, then it will give you the real numbers which are. So basically, this is our P, and so our Pn, then using the transformation T of Pn is equals to the real number. So you need to show that this is actually the linear transformation. So let's look at this. So let's prove this. So what you need to do is you can let, so prove, you can let P and Q, which are the polynomials, to be in our Pn, to be here in our Pn. Okay. Then and C and D to be the elements of real number, to be the elements of real number. Therefore, our Px is equals to A naught plus A1x plus an minus 1 xn minus 1 plus an xn, and our Qx is equals to B naught plus B1x plus B n minus 1 xn minus 1 plus the last one Bn xn. Okay, this last one is plus Bn xn. Bn x n. Then this is where a naught, a1, an minus 1, an, b nodes b1, bn minus 1, bn are elements of R. Then, if we multiply now C and D, CP plus DQ, CP plus DQ of X, then this is the same as CPX plus DQX, DPX plus DQX, which is equal to, now we now bring this, the polynomials of Px, which is the same as C, and then A naught plus A1x plus an minus 1 xn minus 1 plus an xn plus d b naught plus b1 x plus b n minus 1 x n minus 1 plus b n x n. Okay. Then we can now distribute the C and the D. So these are equals to C A naught plus C A1 x plus C A n minus 1 x n minus 1 plus C A n x n plus D B naught plus D B1 x plus D, okay, plus, we can continue plus D, Bn minus 1, Xn minus 1 plus D, Bn, Xn. Okay. Then from here now, we can now take the excess, we can now collect the right terms. So we can collect the right terms here. So we can put the constants together, which is C and this D here. So C A naughts plus D B naughts plus, then we can factor out X in the first one, the X here. So C A1 plus B B1 X plus, you continue like that, plus the next one here is C A n minus 1 plus D B n minus 1, and then plus C A n plus D. Actually, here there is X n minus 1, D B n, and then X n there. Okay. So that is like that. So that is like that. So therefore, we can see that this, when we put the transformation now here, when we now come and put the transformation, now T of CP plus DQ, T of CP, then what we should get are now the constants, which are the coefficients there, which are now the same as CA1 plus DB1, and then it can continue like that, CAN minus 1 plus DBN minus 1, and the last one is CAN plus DBN then, which is the same as factoring out C A1 all the way to AN minus 1, AN. And then here, plus D, B1, Bn minus 1, Bn. And this is actually the same as C, the transformation of P, plus D, the transformation of Q there. Transformation of Q. So if you look at this, the transformation of A naught up to the last one there is equals to what? Is equal to A1 up to the last one. So that means we are not taking the what? The coefficient at the constant. So basically, at the end of it, then we actually ignore this C, which is this one. So basically, GCP is the same as C1, like that. Is the same as now after that. Then it's a linear is a span of span. So that is the proof. So we can say, so T is a linear combination from Pn to R, Pn. Another example, number B. Another example. Show that the transformation C from P to R defined by TP equals to P0 for P elements of the capital P is a linear transformation where we identify R with the one-dimensional vector space, which is, you can write it as R1. R1. So we want to show that C is equals to P0 there. If it is a one dimension, it's a one dimension. So in this case, what we need to show is now if we put the values of, let's say, x in the polynomials to be zeros, then what you get is the constant, which will now be our P0 to be equals to that. So we want to show whether that is a linear transformation. A linear transformation. So we do it the same way, like what we've done in A. So we can let P and Q to be the elements of the capital P. The capital P. And C and D to be elements of real number. Elements of real number. Then we can take our P of X to be equals to A naught plus A1X plus ANXN. And our Q of X to be equals to A naught plus or B naught here plus B1x plus the last one Bnxn. Okay, so we do the same way. Then our Cp plus dq of x is the same as C A naught plus dB naught. That is what we did, plus CA1 plus dB1 x plus the last one plus CAN plus dBn of xn. Now, when we now put now the transformation here and x as 0, then the T of Cp plus dq, the T of now Cp plus dq, if we now put this x 0 here, so the x in 0 here, then basically Tcp plus and that is now equals to what? Is now equals to Cp plus dq, and then 0 there, which is equals to Ca naught plus dB naught, which is the same as Ctp plus dTq. So therefore, this is a linear combination. It is a linear combination. So then T is a linear combination from P to R. Okay, the final example on this, which is C, if we have the matrices, now let's show that the transformation, which is T, and it is an n by n matrix, transformed to m by n matrix, which is defined by TA equals to A minus A transform for A element of M, which is n by n, is a linear transformation where M n by n is the vector of all n by n matrices with real matrix vector space. So show that that is a linear transformation. So we need to show that. So this A is this. So we want to show that it is a linear transformation. So simply what you need to do is just the same way like what you've done there. We can let, so prove. So we can let A and B to be elements of M n by n, and C and D to be elements of V naught. Then what you do is you say T of CA plus DB is the same as, so when you transform this, so we say here T of A is the same as A minus A transform. So T of CA plus DB is now the same as CA plus DB minus CA minus DB or plus, and then transform. So it is the same. Then now you open this. So when you open that bracket there, then it is CA plus DB minus. So when you put the transform there, so CA transform minus DB transform there. And then finally, this is CA. You can collect the like terms minus CA transform plus DB minus DB. So we will finalize that when we meet one. So when connected, so you factor out C, then you find A and AT there, and then B and B. So basically, this is equal to T of C, T of A, and T of B. Okay, see you. I'll post the notes in notes.